欢迎大家来到今天的 Tyra Talk。那我们今天很高兴欢迎到王冠中博士。那他是2010年从台大电机系毕业，然后在光电所2021年从光电所又毕业拿到了 Master Degree。然后他在 Master Degree 的时候呢，做的工作是比较属于 coding， 然后是发展这个indium gallium arsenide 量子点 quantum dot 的 non-equilibrium strings function， 就是 NEGF， 这个也是在它的 title 里面。那如果大家这个不知道 NEGF 是什么的话呢，待会他会跟大家解释。然后他在2014年到2020年的时候，他到了普渡大学，就是在 Indiana 的普渡大学的电机系攻读博士学位。然后他在那边呢，主要的工作是做quantum transport method， 就是量子传输系统的方法。然后主要的 focus 是在这个奈米结构，还有它量子传输方法的应用。那目前呢，他是在Intel 的 TCAP team 工作。那我们就欢迎王冠中博士。可以开始 share。
让我那个 share 我的 screen， 大家有看到我的 screen 吗？
有，可是没有看到 slides。OK，
现在有看到 slides 吗？
有。那我们这 Tyra 的传统还是来做一下，就是我请大家打开麦克风，然后我们用鼓掌的方式欢迎一下王冠中博士。
大家好，然后我可能就是之后会接下来几个 slides 会用英文讲，就是因为之前都是就是那个 technical term 可能会切换来切换去的。然后我这次的大家的 target 的 audience 可能就是如果大家可能对于这个领域啊，然后想要转进来，不管是你是想要申请博班啊，或是你想要就是对于这边有些了解，或者想要用这方面的 tool 的话，就是可以就是感觉是我的 target audience 是那样，所以就是对。然后如果有任何问题的话，都可以就是寄 email 给我啊。然后这些 work 的话，最主要的话就是我在 Purdue 的念博班的时候做的，然后里面的 funding 的 source 可能是什么 NSF 啊，然后 NCSA， 然后另外我领取那个教育部的尖端奖学金的支持，所以说也是这边 acknowledge 一下。然后另外还有跟 Silvaco 合作啊，然后这个 work 也是Purdue 的那个 supercomputer 的，就是我们叫 RCAC， 就是然后所在上面是所运算出来的结果。Okay, and my topic today is optical electronic simulation, and I will go over from the semi-classical to quantum transport, like different perspective. And here's my outline, and I will go over like the motivation and what's the method being used here, and I will show some results. And the methods I will go over the semi-classical. Here's a missing label here, and go over to what's NEGF and what is like Büttiker-probe, and the difficulty of including different processes, a recombination and generation process inside the NEGF. How do we do that? And I will show some results to show, first, like, the importance of including these kind of process, and also I will do a comparison. If we use a semi-classical way to do simulation, or versus like using quantum transport way to do it, what's the difference, and do a summary there. So why are we working on this project is because what we have achieved so far as mankind, like because we have solar cell, and also to harvest energy from sun, and also we can efficiently emit light through light emitting diodes, which is like a really efficient way to transfer energy from electricity to lighting. And to push the boundary further, we need to go, look into what other new materials are out there, what different new structures we can optimize, like the current efficiency, right? And so, for example, to improve the efficiency of LED, like we have like these quantum wells, and then you can see that when we have quantum well, the carrier will like to stay there more, and therefore increase the opportunity to recombine and emit light. And also we are looking to the novel, like new materials, right? Like for example, different Indian composition or maybe some 2D materials, and we're looking into these. So when we are utilizing all these different new material, new structures, and there are lots of quantum effects in it. So therefore, like the current, and we know that the non-equilibrium Green's function, this method, like it's a solving Schrodinger equation with using Green's function, is a well accepted method. So I'm going to go over why do we need NEGF to do it. So what is optical electronics? And so I think the best way to understand optical electronics, like it's just a simple p-n diode we study in school, right? So it's usually a bipolar device where by bipolar I mean like there's electrons and there's holes, and also there are carriers of they're they're in different equilibrium. For example, electron. And they are usually separated by a band gap. That's why we use semiconductor. So having a band gap, and we kind of segregate the carriers to two kinds, and the electron is injected by the source, one side, one contact, we inject the electron here, and the other one is like a hole. And when they see each other, and they can have there's interesting thing can happen, right? Like there are different processes there. For example, there's like Shockley-Reed hole where electron and hole they can recombine, and when they recombine, they can emit phonon, as known as heat, right? So, and this is like kind of a wasteful energy. When they recombine through the defects, the heat is generated and nothing gained. Well, the heat is gained, but it's not that great. And there's like also radiative recombination where when the electron and hole they see each other and they can recombine, and therefore they can emit like a photon. We can see light here, and there's like and the rate it happens usually is, and there's like because like for example, first one they need to see through a defects here, and therefore their proportion is like proportional to the N-type or P-type, because they can one carrier can come to the defect here and to wait for the other person to come and to recombine. So therefore their rate is proportional to either the carrier or either the electrons or the hole concentration here. But radiative recombination, it's you need the rate is proportional to the both of them. So you need to have a high electron here and high hole concentration here to make it happen. And there's like also another process which is OJ recombination, and this is like a 3-particle process where the electron and hole they can recombine, but instead of like emitting a photon, it will kick an electron to a higher energy, or the opposite. It's either 2 electron with 1 hole or 2 hole with 1 electron, but the result is like a waste of energy. And the chance of doing is something like here. And yes， 如果大家如果有问题的话，可以直接问，或是直接暂停一下。然后and the other part is a generation process where the electron hole at this place, at this depletion region, we can absorb the photon and like create an electron and hole pair. So all these processes are needed to simulate an optoelectronic device. So that's what we need to cover when we are doing modeling. So why do we need quantum model? So let's take a look at the simulation result. And this is from this paper I'm co-author with. This is like a simulation result from a commercialized 3.5 LED. And as you can see here, these line here means the density of states, and the color here is the electron density. So the contour line is the density of state, right? So and we can see that the electron is coming from the left side and occupying these states here, and their hole coming from the other direction. This is injected here, and they are going to be in here, and they will recombine and like emit light here. So we can see that if we really do a quantum simulation, we can see that there's interference everywhere, right? For example, all these pattern means if you treat them as particles, it doesn't capture everything, right? So for example, electron, they can tunnel through this barrier and through these interference. So we really need to make use of the quantum transport instead of like the semi-classical way. So the current state of our tool to do this is to, the current way, before I published the paper, right? So the before I was working on this, the best way to deal with this quantumly is also from this paper, where we cut this the domain into different pieces, and then we call some of them the red part and also the green part. So the green part is like equilibrium. And why are they in equilibrium? Because usually the source is highly doped, and then the drain is also highly doped region. And when you're highly doped, there's lots of carrier there, and they will scatter a lot, and there will be, the carrier there will be in equilibrium. So when you are in equilibrium, we can put a Fermi level here, saying, oh, this is the Fermi energy in this region, and this is the Fermi energy, and there's like Fermi level for electron, Fermi level for holes in this region. And there's also the pink part where we do this is non-equilibrium region. So this is like the previous way of doing it, where we do NEGF inside the pink region, and we just put the Fermi level across here. So, but this method has some defects where, we cannot even calculate a simple p-n diode, because a simple p-n diode, we cannot really tell, which region is non-equilibrium, which region is equilibrium. So it's really hard to do quantum transport in a p-n diode when we are doing when we are trying to include all the recombination or generation processes. So there are different flavor of like quantum transport. There's like ballistic NEGF. There's like the one I mentioned is we cut into different domain and try to do the transport calculation. And there's like the super expensive SE form, but none of them can have been like are able to deal with a p-n diodes like with the recombination process. So therefore, a new model is needed, right? And also we can see that this is from a super old paper. Why the recombination process is important is because when you measure IV curve, like there's like different slope here, and they are in the results of different recombination process here, which later on I will talk more about that. So what's the available way to deal with carrier transport? So here's like a list, a roadmap, like where you can pick and choose depending on your needs. So if you are so here the axis, y-axis here is the computational intensity. So I'm going from a super cheap, super fast turnaround time computational cost, like the semi-classical way, and all the way to go quantum, where we need to solve for Schrodinger equation and using the non-NEGF methods. So I will first go over what's the Boltzmann transport equation, and there are different ways to solve it. Like the drift diffusion is the most popular way. It's the first order, I think, what is it, like the first order not approximation, but it's a simplification of the BTE, the famous BTE thing, and that's like we solve it drift diffusion, and then we can also use Monte Carlo like statistically to gather results for the BTE equation. So what's Boltzmann transport equation? It's by saying that there's a distribution function, and by distribution we mean with the occupation of a different state, and what does this means? Like we want to ask what's the possibility of finding a carrier at a particular location, a particular time, with a particular momentum. So if we can, inside, for example, inside a device, there's a different location here, and for each location there is I'm trying to draw this like a momentum. So carrier with low momentum is here, and carrier with higher momentum is on the upper here. And we are asking, what's the distribution? How many particles are in those states? So if we know this information across time, across space, and for different time and space and different momentum, we know this, then the system is solved, right? So, and why is this distribution useful? Because from this distribution function, we can get the carrier density, right? Because if we want to ask what's the carrier density at this location, given the F at this location, we can just do a sum and know how much carrier is here. And if you want to know, for the device you're working on, what's the current, then you just do get their group of velocity from the band structure and you do a sum with this distribution, then you can get, how much current you are gaining at this location. So it's useful because we can get observable from this distribution function. And how do we solve this F? And it's by the BTE Boltzmann came up with this, right? Like the Boltzmann transport equation is the governing equation. So the equation is listed here, and I will just try to show how we understand different terms. For example, the first term means, if you have carrier coming in, coming out, the distribution here will be related to that, right? Because you have carrier flowing into here or flowing out, and the distribution here will be, if you have lots of people coming in and a few going out, then the distribution here will be higher. So this is what the first term means. And the second term means that the F means the electric field, the carrier experience in the charge. And when the carrier is experiencing electric field, it will accelerate and it will change its momentum. So here we mean like that. Okay, given the electric field at this location, the distribution, it's related to the distribution nearby. So a distribution with a lower momentum, with a higher momentum, they can come in and out because of the electric field, like at this location. And the last one is if you have other collision inside a device. For example, a phonon, if an electron can absorb a phonon or emit a phonon and come to this place, if there's a possibility that, then this term is trying to take that into account. So we have all this and all combined, and they can be solved really expensively by doing Monte Carlo, by assuming you have a distribution function and you start to run it. How many carrier coming in, coming out from different momentum space? That's super expensive to do the Monte Carlo. So, but if it's still too hard, then you can simplify this BTE equation to a drift-diffusion equation, which is saying the current at this place is proportional to the carrier with the electric field, and then diffusion with the density gradient. So this is, and the full derivation is in this paper here. People who are interested can go take a look. So I kind of went over the semi-classical way where the carrier and the device are like particle-like, and then they can recombine by solving the drift diffusion equation and the continuity equation. That's how we deal with the semi-classical way. And now I'm going to step into the Schrödinger equation and non-equilibrium Green's function. So we all know about Schrödinger equation. It's like it's given a Hamiltonian of the system, then you can solve it and then to find what's the possible eigenenergies inside the systems. And the Green's function, I still won't go into details. I sorry to disappoint people here, but I think there are really useful material here, and really I think Professor Datas did a really good job on explaining what an NEGF method is with his introductory material on NanoHub. So it's all the information there's a famous book. You can reach out to me and I can show you what's the book you need to read into. But Green's function, from our understanding, Green's function is also in the engineering term, it's like the response to an excitation, right? So usually, Poisson equation, the Green's function. If you know the Green's function for a Poisson equation, then if you put a charge here, what's the resulting potential you can get. So the Schrödinger equation is similar like this. So you put the H side, E side into one side, and then you can solve for the Green's function. And the Green's function is that if you multiply this by excitation, then what's the response you will get inside this device. So here we will first go into the ballistic non-equilibrium Green's function. So first you have this Hamiltonian, and then you can get the resulting Green's function. And then so here it's like the Hamiltonian here, and we can get the Green's function. And using the Green's function, there's some key terms. There's the G lesser, which is the carrier. This is proportional to the carrier density. So it's like here's the excitation you have in the system, and you have like using the Green's function, and there's a GR and GR dagger, then you can get what's the carrier distribution in the device. So what the NEGF does is that we are interested in only this part of the device, and we want to say, oh, we only want to focus on this small region, and then the left, the left we call it, that's a contact, that's a lead, and we don't want to care about the information. There's an infinite, it's an infinite going left and right, they're periodically going left and right. But we don't want to simulate the entire universe. We only want to focus on the transistor or the LED we care about. So given this Green's function, and then we can for different contact, if you're contact to the left, and then there's like a left self energy, and there's like a right side, there's like a self energy here. And with all the self energy on the Green's function, you can get what's the carrier distribution in here, and when they are in contact with the reservoir of a different Fermi level here on the left side and right side here. So but the ballistic and NEGF, there's no scattering, so carrier will not scatter with each other. So how do we do including all these scattering terms in the NEGF? Is like there's a very popular method. It's called Büttiker-probe method, where it's proposed by Marcus Büttiker back in 1980s. So it's a way to mimic dephasing, which means aka the scattering events. So we will try when we're injecting the carrier into the device from the left and right side. So we're adding more these reservoir inside the device. So we're taking the electron out and put it back in, take it out and put it back in. So in this way, we're mimicking like carrier. We can randomize the carrier, and the carrier's momentum will go around, and like you can see that this is more closer to the real world problem where the device have scattering. But this method was only applicable to a unipolar device. For example, if you only have electron here, it can only simulate electrons scatter inside the device. So my work in my PhD was like to ask the question whether we can modify this for a bipolar device. Bipolar means so when we have so can we put like two when we are we simulate electron and hole separately like before, right? We have electron coming in and electron coming out, and we also simulate the hole, whereas hole coming in and hole coming out. And we also include these probe here to extract the carrier out of the device and put it back in. And this way, if we somehow take the carrier out from both electron and hole, and that's equivalent to semi-classically how drift diffusion model the Shockley hole and different processes. So using this method, we can cover the processes I mentioned in the optoelectronic device. We can model Shockley hole, we can model radiative, we can model OJ, we can model all these effects inside the Büttiker-probe, enhanced Büttiker-probe method. So here is like all the methodology I've mentioned, where from cheap to expensive, we have like drift diffusion, Monte Carlos, and the NEGF, and also in the NEGF we have like the ballistical one, and also the what's the time now? Sorry, do we still have time? Oops. Oh, 5:40. Sorry. Let me put it back on. Yeah, so we have like all the different methodology here, and this is the one I was mainly working on. So carriers, they are wave-like. So for example, from before drift diffusion and Monte Carlos, each of the carriers, they are particle-like, and then we are solving the current continuity equation. And for each location, there's like a quasi-Fermi level, which means they follow Fermi direct distribution. And quantum correction with artificial Oh, and there are ways people use when using drift diffusion, you can couple it with quantum correction, like solving Schrödinger equation in a certain region, and then couple them with the drift diffusion and try to mimic it. But it's kind of like you will have artificial boundary condition, like when do we choose? Which is the part we want to solve at quantum? Where do we solve semi-classically? So there's lots of confusion if you're coupling that. But using NEGF, like if it's ballistic, it's not really useful for optoelectronic because there's no recombination scattering processes, and there's like the way I mentioned, it's called multi equilibrium and equilibrium way. So some part of it you simulate, you assume like there's like a equilibrium there. But this method, it requires like a really it only works with, for example, quantum well structure, and then inside here we can set it to be equilibrium and somehow to have the carrier recombine. But in this way, the new proposed Büttiker-probe way, where the carriers are always wave-like, and we can have recombination generation everywhere in the device, and we also can have scattering consider, and you don't need to say, oh, this part is in equilibrium or the other part is not in equilibrium. So you can simulate the entire device without artificial boundary. And of course, like there's the SE-born method, but that's like super expensive, and no one has, I would say like no one has done like a simulation like LED kind of simulation like with it. And so later, next one I will go to talk about the results. So first part, I will show that the importance of recombination. So here is a picture showing, this is a structure where electrons coming again from the left side here, and then there's a band structure. There's a band gap in between in this, and I crop out in between, and the hole is coming to here. So there are two paths that electron can. There's a current conducting path, right? So one path is the blue path where electron come here and the hole come here, and they will recombine. And this is a current, they can form a current path. And the other path is the black line where the carrier come in and can jump over the barrier to the other side. So there are two ways that the carrier the current can form. So here's a comparison with or without this indium gallium nitride. So when we form the quantum well with a lower band gap material here, so on the two sides gallium nitride with a larger band gap. With indium gallium nitride, you can shrink the band gap, and that's why we see this dip here. And with this, you can see that comparing the two, the recombination current is much higher with a quantum well, because inside a quantum well, there's a higher chance of carrier here, and because we all also know that the recombination is proportional to the carrier density there, right? They want to see each other, they want to recombine. So the more they have at each location, the more they can recombine with each other. So so here I'm trying to show that when we do any NEGF calculation, when we include the recombination here, so this is a typical IV curve, and we can see that this is a log scale current, right? So when we increase the drain voltage, we are pulling the barrier down, so there are more and more current can go through to the other side. So let's focus first on the low VD side. So on the low VD side, there you can see that there's still a barrier here. So the black current, so the total current will be, as I said before, there's like two parts. There's a recombine, the electron and hole, they can recombine here form a current path. And there's also the thermionic current where the carrier can jump over the barrier to the other side. So this is a two part. And when the barrier is still high, we can see that the black line is not in favor because it's hard for electron to jump out here. There's like a few particles there to jump out. So the black part of the current is super small. And at this region, the recombination current dominates. So we can see that this is the distribution here. And when we increase the bias voltage, we're pulling the other side, the barrier down. So as you can see here, right now the black path is easier, right? The electron can zip through the device and form a current path. So right now, the blue one it's still large, but compared to the black one, it's much smaller. So that this is the on off. So when we include NEGF, when we do non-equilibrium Green's function transport calculation, when we don't have recombination, which current do we get? We get the we don't have the blue line here, right? So we are only getting the black. And if we using this method, we are able to include the recombination process, which means we get the red line. So we are pushing the boundary of NEGF like such that we can simulate the device from a black line to a red line, which is a really large difference if you look at here. And if you look at the which is like before the threshold voltage, there's a huge current difference with or without recombination. And it also further impact what's the threshold voltage. The threshold voltage means like when is your device on or off, right? So there's a small shift here, although on a linear scale, but with more recombination, the red and also the black line will have a larger shift and therefore a larger impact. So it's really important to include the recombination in your device. And next I will.
Question here. Hi.
Yeah, sure.
Hi. Can you go back to your previous slide? Yes. Okay. Maybe this is a bit stupid, but I thought I thought like recombination means you have electron-hole pair recombine, and I thought it will lead to, let's say, emission of phonon or emission of photon. And usually, I would think recombination is bad for the current, but here you are saying when you have smaller bias voltage, the VD is smaller, you actually have a higher recombination energy, recombination current. Why is recombination contribute to a current?
To a current or a current?
Okay. To current.
So there are different recombination process, right? There's like I mentioned, like there's a Shockley-Hole recombination, there's radiative recombination, and there's OJ recombination. So they are all the consequence of electron-hole. I mean, OJ is the radiative and the Shockley-Hole is one electron, one hole, and they disappear. And the Shockley-Hole is you emit heat, so you're losing.
Yeah, phonons. Yes.
Phonons, and then radiative is like you emit photon. Yeah. And OJ is like you kick another carrier to a higher energy, right? So it's useless too, right? So not all. Okay. So wait, your question is, but here is showing the recombination is the blue line here, right? So when your lower VD is lower, when your higher VD, it's higher. But sorry, what was your question?
My question is, I thought recombination is bad for the current.
Why? It's bad because it's I think bad is kind of like a subjective, right? I would call it bad if I would call it this is a bad device if most of your recombination happen in a way, the Shockley-Hole way or OJ, right? So the black and the red is bad because they don't produce photon. You don't produce light. Then why are you recombining? So I think bad is okay. It depends on which process you're looking at, right? I think the blue one is good because
I see because you want a photon going. I see.
Yeah.
Okay.
Yes.
Okay. And the relation between maybe this is a bit specific, like OJ one, the radiative one, and the phonon one, black, blue, and red. Are they always in this order? Won't they cross at some point if you have different lengths of the? I think this X means the size of your. Yeah, because it looks like you always have red, blue, and black. Do they ever cross at some point?
I think I was showing. I think this is an interesting question because I was showing previously they have different relationship, right? So this is an ABC model where the Shockley-Hole, they're proportional to n plus p, and the radiative is N and p, and then the rate is proportional to n squared p. So I think if you engineer it smartly, you can control which one dominates. But somehow in this scenario, the red one is always larger. But if you look at the equation here, right, like it's n squared p. So if you make the p much smaller, right now it's equally large. N and p are super large, both in here. But the real device, I think it's more complicated. And maybe in some way, smart way, you can make the blue dominant and the other two are, because relatively they are different, right? They are not as, like in this case, the red are closer to blue, but here you can see that the red and blue is farther away. Or I think there's some way we can engineering like to make it some area the blue one will dominate. Yeah. Question. Okay, and is there any other questions?
Oh, I have a question here.
Uh-huh.
So I guess this case is simple enough. I guess this is probably just your test case, but this case is simple enough that you can also use semi-classical way to do a simulation. So I'm just wondering, like, how do they compare?
So that's my next topic. Is like comparing on this really small structure, and then we're using a semi-classical way and also a quantum way to compute them, and then I will show some comparison here. So I think that will answer your question.
Okay, great. Yeah.
Okay, so the next one, as the question has elevated us to this point. So I'm going to talk about the comparison between the two, semi-classical and quantum. And how do we compare? How do we make a fair comparison? Yes, that's an important question. It's that we use the same small, like the structure I was showing here is like 20 nanometers. So it's a super tiny structure. And then I'm going to apply semi-classical method, the drift-diffusion one, and also for the quantum way, I'm using this new method, the Büttiker-probe with recombination generation method, which is in the tool our lab used to work on in grad school. So if you guys are interested in applying for our group, email me and I can give you more information. So how do we compare this? Is that in all the transport simulation, like we're decoupling the transport part with the part like electrostatic part. So we usually do a self-consistent. We solve for where's the electron holes, and given the electron holes and they have charge and therefore they will form a potential. So we will feed it back the carrier transport and plug it into Poisson and get a potential, and like doing this 100 times or whatever until it's converging. So it's like self-consistently solving, decouple the two and solve the Poisson, and then just keep on doing until it doesn't change anymore. And then we declare this simulation is finished, it's converged. So to compare, it's easy because we can just focus on this part, and then for the carrier, we can choose to use NEGF, or we can choose the semi-classical way of doing it. And when doing the semi-classical way, we also choose because drift diffusion, to solve these problems, they usually have another quantum correction model where they are solving just a confined Schrödinger. Like NEGF is more like an open boundary Schrödinger equation. But like for semi-classical people, they usually will couple it with like a quantum correction method, which is like solving Schrödinger inside a infinite quantum. So they will have boundary, but solving Schrödinger only in that region, and try to couple them together. So the question to answer is how do we compare the quantum and semi-classical models? And here is more of like showing, so the left side is using the NEGF, where we will have a band structure, right? Like we will have the band gap of, I think this is like around 0.4 to 3. So gallium nitride is like 3.4 electron volts. And inside here, there's like a quantum well. So the actual epitaxy will be gallium nitride, and then we assume that it's doped with 1E20, and there's like a region of indium gallium nitride, and that will have a smaller band gap, and also the gallium nitride. And this is like the structure we are looking into. And in the NEGF, we will provide like a full energy. So the y-axis is the energy range, right? So So you know here are some states that can be, so here the color means like the density of states, it means like the carrier can have the possibility to go in there. But there is some portion of it like brighter, which means because of the interference, carrier doesn't have a, even if you have carrier, it cannot go in here. So that's what the density of states means. So the NEGF we can provide, it's non-equilibrium throughout the entire device, which means the carrier doesn't have to follow Fermi-Dirac distribution everywhere. And also we can see that the states is broadened. So because you are in contact with the external source, therefore the state is not, it's broadened. Otherwise, if you solve this in a Schrödinger equation, it's going to be confined. Like, oh, the part like a state is like, it's not broadened. But here you can see that, for example, quantum well here, it's not a compared to Schrödinger equation, it's a fixed energy level because you're in contact with the surrounding. Therefore, there's a peak here. And for the drift diffusion, we can see that here, drift diffusion equation assume that in everywhere there's a Fermi energy, right? And for this Fermi energy follows the Fermi distribution. So which means the carrier will be Fermi distribution everywhere with different Fermi energy. So also we are solving the quantum, using this QWell method in Atlas, which is solving Schrödinger equation here. So that's why we can have this red wave function squared here. So that's the wave function form. And how is it solved? It's by solving Schrödinger equation only in this region. So we are defining a region where we want to solve this closed boundary Schrödinger equation. We are trying to couple this to the drift diffusion methods. And there's like several parameters. For example, in a drift diffusion, you have ABC parameters for the recombination, like the Shacklery hole, the photon, and also the other ones, the OJ. So there's like the parameters for it, and we are using the same ABC. And in drift diffusion, there's like a mobility term where for an NEGF, it's called self-energy, which is the scattering rates in the device. And that will, in a semi-classical way, that's called the mobility. So we need to find a corresponding, given this mu, what's the scattering rate in the device? And therefore, what's the self-energy we are using in NEGF? And for drift diffusion, when you are, there's a density of states, and you are assuming you will, get a carrier. So there's a, for different m, for different effective mass, you correspond to different density of state, and therefore carrier. For NEGF, we are using, we can support tie binding, different way to describe this EK relationship. So that's the corresponding, right? We can also use effective mass, or we can use tie binding method, or KRP, or linear functions. And so the basis, there's a little bit different. In drift diffusion, we can only support so this is how we couple them. So I'm going to show that the direct comparison, like from observable, we can see, right? So for example, on the right side, this is showing the solid line is the drift diffusion results. And you can see that this is the carrier density across the device. We have high electron on one side, and we have high hole on the other side, and they are penetrating into each into the other side. And we can see that the drift diffusion here is much lower. Like this is log scale, so it's like 10 to the 5 times smaller than the quantum transports method, right? And the reason is understandable, because when you look into here, the electron, the NEGF, you can, what is it like, when you bounce a ball to the wall, the semi-classical will bounce back, but quantum you can penetrate into the wall, right? So you can see that analogy here, where you still have some density of states inside the barrier, where the semi-classical will just say, oh, there's nothing. You bounce into this wall and you will go back directly. So this is like the ball analogy for, so that's why when you're doing quantum transport, this carrier inside here is higher, much higher, 10 to the 5th time higher, because of the penetration here. But otherwise, like, the potential is pretty matched here. But the carrier difference here will cause you to calculate the recombination rate different, right? Because you have a higher density, then therefore your recombination rate will be different. So that's why the potential looks the same between quantum wave and semi-classical wave. However, the recombination rate calculated from which is a post-process using ABC model to predict, what's the OJ, the photon, and also the OJ related process. There's a huge difference and lower bias. You can see here, the quantum wave, because you have more penetrated electrons for them to recombine. Therefore, you have a much higher recombination rate. And for higher bias, they're pretty much similar, but small difference here. Okay. And this case, before I was talking about a HOMO junction where we're using gallium nitride all across, but with different doping. And here is a heterojunction where similar things are done. We're comparing the carrier density, and we can see that, there's some difference here, right? Like the semi-classical, we have a sharp discontinuity, probably because we chose a boundary, different, but which part should we solve Schrödinger? It's pretty subjective. So I'm putting all the things here and seeing that there is an impact, like with or without drift diffusion, like or NEGF, like what's the impact on carrier density. And here is trying to show the recombination with in this heterojunction. We can also see that because drift diffusion coupled with Schrödinger equation, therefore we can see that the recombination rate after doing this is pretty similar. So I think this is like a positive side about drift diffusion. It's pretty fast, and with coupling to like quantum correction, it's matching NEGF pretty well. So it's like also kind of giving confidence, but also saying like, drift diffusion is not that bad. Like you can still quantumly correct it with the solving Schrödinger in partial region. Okay. And here I'm trying to show the IV difference for a homojunction device. So in a homojunction device, if you measure the IV curve, and here the solid line is the drift diffusion, and the circle is the quantum wave, and we can see that the off current, like this off current, there's like a larger difference between them. And if you compare the heterojunction device using the and there's some difference here and there, but just like providing the comparison here. And this method, we can further, we're enabling NEGF to be able to solve like carrier generation, because we are injecting we can assume the light come in and producing electron-hole and give them, separate them, and then to generate current here, right? So here's the simulation results, like using NEGF, and this is like the first tool that we can cover all processes including generation, and then to enable a device simulation. So here's a summary. I kind of review different carrier transport method and all, from BTE all the way to NEGF, and providing the references there. So if you're interested, you can email me for more information. And this work is to propose a really generic method for recombination generation process inside the NEGF framework. So we're enabling the NEGF community to approach a problem like recombination generation. And we show the importance, for NEGF with or without recombination, what's the difference and why do we need it? And we also benchmark against like drift diffusion based TCAT tool. And to see that, we can see that the charge is different and without methods. And also we can show that there's tunneling and wave phenomena here. And I know, 然后就是最后对啊，如果说 Tyra 有些什么读书会啊，然后或是想要讨论这方面的话，我就觉得都很高兴跟大家讨论。然后如果有问题的话，或者是就是关于一些这方面的问题的话，都可以 email 给我，对啊。OK， 大家都还在吗
？OK， 还在。那我们先就是大家请打开麦克风鼓掌，感谢一下就是观众。那我们现在有没有问题吗？就是想要现在提出来的有没有问题？有问题就直接开麦克风讲。对，
没错。
好，那好，我想要问一个可能没有那么有关联的问题，就是我好奇问一下，先好奇问一下你在 Intel 多久？
1年多吧，差不多。
那你会需要，就是你在做这些 simulation 的时候，你会需要常常跟做实验的人做一些沟通吗？
有一些人，但这个不是我 Intel 的 work，这是我博班的 work。然后
OK
Intel 的话，对，我觉得会跟做实验的沟通吧，对。
对，
就比如说他们有些
因为我很好奇，
数据，
你
就是他们有些
就是
数据，
这一套
嗯哼
simulation，就是当你当你要解释这些 simulation 跟实验的人沟通的时候，就是你有没有觉得会有一些 gap 之类的？会不会
我觉得
很困难？
会耶，可是我觉得他们就会把问题划到说，就是对啊，就是不会，如果对啊，就是找你的话，可能就是觉得说这可能会有相关，可
就是
是
比如说那像比方说，就是你们就是像这些 simulation 做出来，最后要跟实验讨论的时候，是可以跟实验比吗？还是说有一些什么 trend 是拿去来解释实验？就是你怎么样拿这些东西在跟你做实验讨论的时候，就是你为他们做，你可以就是你怎么跟实验合作，就是你的模式啦，有点抽象，我也不知道怎么解释。像是有一些像是比方说是用这些 tool 之后可以发现是实际可以去解释他们的数据吗？或者说你们是可以提供说根据这个数据，也许 improve 的方向或者什么之类的，这是做得到的嘛？那种感觉，这样不好意思，有点抽象，就有点
我觉得是
好奇啊，这样。
我觉得是譬如说，我用博班举例子好了，就是博班的这
对，
个 project，别人可能就说，哦，会不会是因为你 recombination 的关系，然后造成电流变小或变多？那如果说你把这个 defects level 变大或变小，就是可能我觉得是比较是trend，就是说，如果你增加这个 defects 的话，你可不可以看到这个 curve 往那边 shift？可能不能100% match 那个实验的 data，可是你可能跟他说，哦，如果是这个现象，这个 defects 变多，那我的 recombination rate 会不会变大或变小？对，你可以做实验，然后做实验跟做模拟上面的话，可以去，我觉得很多问题都是没有那么，就是你需要去 model 去弄出来，你才能说哦，真的是这个现象。然后就是
嗯哼，
你做实验可能观察到哦电流变大了，可是你不知道为什么，那可能你可能说，那如果你 model 里面也去做这个调整，或是做对加 stress 或是有很多东西可以去变化嘛，就是你模拟的话，你就有很多参数可以去变化，你可能是调整 defects level，可能调整什么各式各样的参数，那你去 confirm 说你实验说我觉得这个部分的 feedback 是蛮重要的，就是对于说
嗯哼，
identify 你说的对不对，到底这 simulation 的，我觉得可以去验证说到底是不是正确的，对啊，
哦，
嗯。
那在另外一个好奇是，我知道你现在讲的是你博班做的啦，所以我有另外一个好奇是你进 Intel 之后，你感觉你跟博班做的东西有差很多吗？
我觉得差蛮多的，就是感觉，
真的，
对啊，对啊，差蛮多的。
真的哦。所以
啊
即使是已经是，因为我看起来这玩意儿就是进入就已经到了可以虽然说可能是比较 simple 的 geometry，但是已经是可以到算真的 device 的quantity 了。那你进去之后还会发现，是因为就是我有点那个这种差很多，是指说只是单纯的研究领域不一样的，还是说
我觉得
其实这些 tool 进到里面，
我觉得形式差不多，形式的话，大部分就是看 paper 啊，然后看说
嗯，
有什么 model 可以去使用，然后可是就是感觉博班的话，就是教授跟你说做什么事情，你就把它做出来嘛，或是你去就是感觉比较 specific，可是公司的话就是不知道，我觉得很难
哦，你是讲这个，
一言，
哦，OK，
对对对对，
算了，我也自介一下，因为我也是 TK 部门的，我现在在台积电工作，
OK OK，
对，所以就是
哦，
我其实也是我对这边也是有一些了解啦，然后但是我现在的也许不应该在这里问，只是说我的困扰通常都是那种，就是当你要跟实验沟通的时候，实验总会讲说，哎，你怎么到底算是对的？然后
OK，
你跟他讲这些东西，就会觉得就是要讨论起来，总是觉得有一种很困难的点在。我不晓得在 Intel 里面会不会有类似的感觉？啊，
我觉得
对不起，我应该
不同公司可能会不同的，就是像我觉得我不会直接去跟实验，事实上我不会直接跟实验人接触，可能是透过一个中间人去用这个托，就是感觉可能有分工，可是感觉对吧？对对对，
了解。
还有其他的问题吗？
我想问一下，就是这个，就是你现在模拟的这个东西，感觉看起来就是很简单，然后看起来这个用 Boltzmann transport 的 equation 好像也可以做得出来，就是虽然你要加一些 approximation 之类的，但是就是我在想说，这个东西的好处是，譬如说以后在比较困难的 device 上可以比较有效，就是。
可是我觉得BTE 的话，你就无法有这种就是你是假设它是 particles 嘛？那如果 particles 的话，你说这种细节这种 simulate 出来吗？对 simulate 不出来啊，对不对？所以你说你是 particle 假设的话，你就是很多 missing 掉很多 detail。可是我现在秀的结果是说，有一些 drift-diffusion 是差很多，有一些是差不多，但是让我意思说，就是你怎么知道你的 future device 可能是 2D materials， 可能是什么的时候，对吧？就是你会不会 miss 掉一些 important 的 details？大概是，所以我觉得 BTE 是无法去取代，就是在这个小 device， 连这个小 device 你也无法去做 BTE 是正确的。那你刚刚说 BTE 还是 drift diffusion？对吧 ？drift diffusion 的话，你说真的是 solve 那个 Monte Carlo solve BTE， 但是就连那样子的话，你像这种interference 啊，或是这种 tunneling 的话 ，BTE 是你需要你是弄不出来嘛，你可能就要放很多 correction model。BTE 的话是说你 particle 怎么样去 scatter， 对不对？那你可能就要去 calculate 说，就是你要加很多 calculation 进去。可是你 NEGF 的话，就是你把 device 丢进去，然后它给你的结果，你就知道说，这边是 low density of state， 这边有这种 pattern 出现，这种 interference 的 pattern， 但是这是 BTE 看不出来的。
OK， 我想到。
对啊。
但是你画的这些图这个是 equilibrium 吗？就是你
这边是
density
of state
下面的
什么意思？
就 density of state 是在 equilibrium 下的 density of state 嘛，对不对？
没有 ，density of state 跟那个是不是 equilibrium 是分开的嘛？因为你 density of state 是说你有这么多 states， 对不对？那你 equilibrium 是说你有一个 distribution function， 对不对？你有就像 Fermi-Dirac distribution 是说你底下可能是1，上面可能是0，然后这样慢慢下去嘛。所以你 given 这个 density of state， 然后你去填那个 Fermi distribution 嘛，对不对？那你 drift diffusion 的话，drift diffusion 的话是说你是任何 device 的位置你都是 Fermi-Dirac， 然后你可能我画一下好了，等于说我看一下有没有哪一张图是比较好的。对，像这个图的话，你说 drift diffusion 的话，可能是你会有个 Fermi level， 对不对？你可能说这边是 Fermi level， 那你的 distribution 就是说你这边是1，然后这边是0嘛，对不对？这是 distribution 嘛，0到1嘛。可是你任何位置你都是被这个 Fermi level 绑死，然后你可能就是你可能 Fermi level 这边低一点，因为你 Fermi level 这边可能降下来，然后你说我的 distribution 可能是这样子，然后到这边可能有一些小变化。可是 NEGF 的话是说你 carrier distribution， 你任何一个地方都不一定是 Fermi distribution 嘛，你就是非常的自由，就是你 particle 你想要高一点，你想要低一点，你这边 distribution 可能是这样子，不一定是 Fermi distribution， 对不对？可是像我们是跟 contact 绑定嘛，等于说你 device 中间到底是不是，对不对？它到底 distribution 会变多少？因为你注进去的 carrier 是从左边，等于是你左边这边是 Fermi distribution， 对不对？这边是 Fermi distribution 注进去，可是等到你 carrier travel 到这边来，你会不会变掉？你经过 bounce around 这边对不对 bounce 过去，你可能就不是 Fermi distribution 了。所以这是 NEGF 的优点嘛，就是你不会受这个 drift diffusion 的限制，说每一个你都被绑死，说你要这样去 distribute， 对啊。
OK， 了解 ，OK。
OK， 那还有问题吗？ 没有的话，我想问最后一个问题，就是你在倒数第2个 slide 的时候，你有讲到photon absorption。你这边的 photon absorption 是只打在中间的那个 junction 上面吗？还是说你整个系统都有受到 photon 的影响？
这边是一个 toy model， 所以我只打在那个绿色的地方。我应该是啦，可能要详细可能要看这个，对，后来我发另外一篇 paper， 不过就是对我当初的假设是说只打在某个地方这样子，就是大概是从这边到这边有加光这样子，就是加了 generation rate。
OK， 那你的 photon 是怎么处理的？是把它当做一个对，你 photon 是怎么处理？
我没有模拟 photon， 就是模拟说，因为这个 photon， 所以这边的电子跟电动每秒会跑出来多少，所以我就是没有模拟 photon， 就是假设 photon 被吸收，对吧？就是一颗 photon 进来，可能就是根据这个，
你就是把它往上移一个 h bar omega 这样子吗？就是吸收了一个 photon， 它的 suppose 它能量会往上移一个 h bar。
那所以我现在应该是假设这个 band gap 嘛，这个 band gap 可能是这个 band gap 是 3.2 eV 嘛，可能会是3多少 eV 不知道，假设3 eV 好，就是我假设说有一个3 eV 以上的 photon 进来，对不对？那你就可以把 carrier hole 这样分，就是产生 electron-hole pair， 然后是因为这个
OK，
对。
所以你就一开始就假设 electron-hole pair 就 electron-hole 已经 separate， 然后开始做你的 simulation。
对
OK， 了解。
对。
好，那现在还有问题吗？大家没有的话，那我们再谢谢一次冠中，那我先
谢谢，
我就先关掉这个录影。